Okay, thank you for introductions. And I'd like to thank the organizer for kind invitation to this nice workshop. And actually, this is my first visit to Vienna, so already I have enjoyed seeing and so on. In any case, I'll talk about this title, 60 Supergravity. This talk is based on the work with Gregory, who was here in last week. Let me start. So yeah, there are many approaches to the Swampland program. So here in my talk, I will hold this type of approach. It is as follows. I will first try to understand the Swampland bound in a controllable situation. It means that theories with higher supercharges. Then we try to gradually reduce the number of supercharges to approach to our world and to understand the Swampland bound in a better way. So for instance, if we start from the string theory, toroidal compactification gives the maximal supersymmetric theories. And if we want to reduce the number of the supersymmetry, we put the theory on Calabian K3, Calabian 3, Calabian 4, and so on, or flux, adding a flux. And then number of the supersymmetry becomes smaller, and eventually we will want to go to our world, which is non-supersymmetric. So already there are several attempts along this type of approach. For instance, okay, this is a rough cartoon about the current status. For instance, 32 supercharged case, maximal supercharged case. So we have more or less good understanding. It is just a M theory or type 2 theory on a toroidal compactifications. So even for the half maximal supersymmetry, 16 supercharged case, we have not complete, but a good understanding about what rank of the theory is allowed and so on. Although in some cases, there is still controversial, but more or less we have a good understanding. So in this respect, I want to go to the 8 number of supersymmetry, whose maximal dimensions are 6. So this is a target of my talk. So what changed from maximal supercharges to 8 supercharges? So in 32 supercharged case, theory is essentially unique. So if we say that there is a massless gravitons, so all the massless particles are determined because it is just a one multiplet. So if we go to the half maximal, we have a freedom to add the vector multiplet. So this means that in addition to the requirement of the gravitons, if I specify what the gauge group, so theory, at least a massless spectrum, level of the massless spectrum, it is determined. So then what happens if we go to 8 supercharges? Then we have additional freedom to add the hypermultiplet. So that means that we have the additional choice to choose the gauge group and representation under it. Okay, the broad goal of my research is to understand the landscape and swampland of the 8 number of the supersymmetric theories. So to be specific, in this talk, I will talk about my recent work along this line of things. So first, we try to identify what is a consistent supergravity landscape. As I will show in a moment, actually there is a very intricate, complicated consistency conditions, and it is not trivial to identify what's a consistent effective theories. Then after that, I will talk about the quantum gravity bound on it. So to be specific, I will use a supergravity string bound, which first proposed in these papers. So, okay, let me start from the first part. So let me first quickly recap what the ingredient of the 6-dimensional supergravities. So there are 4 supersymmetric multiplet, gravities, and tensors, and vectors, and hypers. So for instance, there are 2 modular fields, massless scalar field in a tensor multiplet and a hyper multiplet. So the vacuum parameterized by the tensor branch scalar is called a tensor branch. And we often use the notation J. It is a vector in a R1, T spacetime with one constant j dot j equal to 1. So, sorry, t means the number of the tensors. And 1 plus t number of the degrees of freedom with one constraint to describe the t number of the scalar field. Also, yes, vacuum parameterized by the hyper multiplied scalar is called the Higgs branch. In any case, this is an ingredient of the 6-dimensional supergravities. And then let me tell you about what are consistency conditions, EFT consistency conditions. So there are 3 of them: anomaly cancellation, and positivity of the gauge kinetic term, and unimodularities. So first condition is anomaly cancellations. Okay, because it is 6-dimensional theory, anomaly polynomial 8 form, the rough form is something like that. And as usual, there are 2 contributions. One contribution is a one-loop diagram coming from the chiral fermions and the chiral B field. Chiral B field means self-dual or anti-self-dual B field. So on top of that, we also have a contribution from the Green-Schwarz type mechanism. So namely, it is a tree-level B field exchanges, where I parameterize the coupling by the B0 and BF. And this gives us a contribution like Y4 squared, where Y4 is given by that. Requirement is that the sum of them must vanish, or anomaly freeze. Okay, the formula is summarized in this. So it is a bit complicated. But detail is not important, but there are conditions like, for instance, for the gravitational anomaly free cancellation, we have the number of the hyper minus number of the vector equal to the this number, where t is the number of tensors. So to cancel the other anomalies, we have to put something. And here, each number is not so important, but the only important thing is that these numbers are completely determined if I fix matter spectrum and matter charges and so on. Okay, this is the cancellation of the perturbative anomalies. So in principle, we have to also care about the global anomalies. So for instance, in a recent understanding of the global anomaly, we first need to understand what a Borodism group. So if we take a spin structure of it, we know that many of the Borodism group vanishes. So while in old sense, I mean homotopy group, there are several remaining potential anomaly, but Borodism group is vanishes. In this sense, okay, at this level, there are no global anomalies. Yeah. Yeah, the reason is the gravitino is chiral. Yeah. Yes. Okay. And if you think about this level, there are no global anomaly. But I don't think about the global anomaly issue in this talk. But I also want to note that this might not be an end of the story, because the correct structure to impose is not spin, probably, because of the Bianchi identity. We have to put the twisted string structures. But if we put this, the complete understanding of the global anomaly is still open, as far as I understand. But with this caveat, I do not think about the global anomaly, and I only think about perturbative anomalies. So, okay, there are 2 additional consistency conditions. So one is the positivity of the gauge kinetic term. It is quite simple. So sign of the F square must be positive or negative in my convention. But that means that J dot B is positive. So B is a coupling between B field and F squared. It appears in the Green-Schwarz mechanism. And J is a scalar field in a tensor branch. So yet another condition is a unimodularity condition. This is a bit more non-trivial, but it is EFT consistency conditions. So to explain that, I first think about the lattice spanned by this BI vector. This is called anomaly lattice or tensor charge lattice and so on. But in any case, we can think about this lattice. Then the requirement is that this lattice must be embedded to the unimodular lattice gammas. That are conditions. The condition can be understood in that way. So, okay, if we start from the 60 theories, and there is a chiral B field, self-dual or anti-self-dual B field, then we can think about a surface operator used by this. Here, sigma 2 is some two surfaces, and nu are the charges. And then compactify this surface operator on torus T2s. So yeah, there are several ways to reduce this surface operator. For instance, if we reduce one of the leg along the one cycle of the torus, I get a Wilson loop operator in 4D. And if we reduce it to another cycle, we get a two-foot operator. Then this Wilson operator and two-foot operator must satisfy the Dirac quantization condition. So it is translated as this charge should obey the kind of Dirac quantization condition. It is nothing but the unimodularity conditions. So yeah, this is why we should require these conditions. Okay, then I have enumerated what the consistency conditions. Then we want to think about what the possible theories. So we want to perform the classifications. So far, what is known is that when the number of the T is less than 9, then the number of the anomaly-free six-dimensional theory are finite. And moreover, for specific gauge group, so SUN or specific representation, like a fundamental adjoint, partial enumeration for the theory was done. Then what we have done is the following. So we have considered the following situation, any gauge group with any number of the simple factors. So SU, SOs, and expressional group, and so on, anything. And we also allow the any representations, like, I don't know, 2 symmetric, 3 symmetric representation, and so on. Okay, this is what we have done. And also, we still have some technical limitation, like we are not able to include the U1, SU2, SU3 simple factors. And this is a really technical remark, but we have to omit several choices of the gauge group and yeah, hypermatchplate. So, okay, let me sketch classification ideas. So to classify the theory, so we characterize a theory by using a hypergraph. That means we have the ingredient as the vertices and edges and surfaces and 3 edges and so on. Then we express the gauge group by vertices. So say this is an example. Say this V1 represents SU4 gauge group with this hypermatchplate, and V2 and V2 are the similars. Also, this edges describes the hypermatchplate, which is charged under both V1 and V2 gauge group. For instance, this edge corresponds to the here. Describe the hypermatchplate, which has a charge 4 here and 6 here, and plus 4 and 14 here. And the other edges are similar. So we can also think about a surface. It is denoted by E1 superscript 3. So this describes the hypermatchplate, which is charged under 3 gauge group. Like, okay, this is a hypermatchplate charged under all of them, SU4, SP3, D2, and whose representation is like this. So yeah, we can, in this way, we can write down the theory by using the graph, hypergraph. And the point is that when this graph is too large, such a theory is not allowed because of the gravitational anomaly-free conditions. So, okay, each vertices has a value delta, which is a hypermatchplate minus vector matchplate. The total number of this is upper bounded because of the gravitational anomaly-free conditions. This means that if we put too many number of the vertices, such a theory is too large well, too large delta, which exceeds the anomaly-free conditions. Therefore, we can do the following classification scheme. So first, let's consider a theory with one vertices, just a one vertices. It is a theory with one gauge group. And then put the another vertices, and let's consider the all way to connect between them. So this describes a theory with two gauge group. In a similar way, we can add another vertices. We can think about the three gauge group with edges or hyper edges. So we can enumerate the theory in this way. But eventually, at some point, we failed to satisfy the gravitational anomaly-free conditions. But the important thing is that in this way, we can enumerate what's a possible theory until we hit the gravitational anomaly-free conditions. So this is a strategy. Okay, then using this strategy, we have the following result. In the following, for simplicity, I focus on the T=1 cases. But in the paper, we consider the cases. For T=1 theory, we found this number of theories. It's 600,000 number of the theories. Yeah, and let me say some statistics, not statistics, but some features of this ensemble. For instance, for T=1 theory, the largest gauge group are the following. The largest dimension with a gauge group is given by this theory. Gauge group is SU16 times SU32, so whose dimension is 1 to 7, 8, and hypermatch-plate are given by this. Similarly, largest rank theory is given by this one, SU18 times SU6 to the 6 powers. So this gives rise to theories with 47 ranks. Also, the ensemble can be simplified by thinking about the Higgsing. So because they are hypermatch-plate, many theories are connected by Higgsing. Like, yeah, this is one Higgsing tree. We start from the SO32 times the SO8 theory. By adding the web to the one of the match-plate, I get smaller gauge theories. In this way, there are special type of the theory, which we call the source theory. This source theory is the one which do not come from the Higgsing of another theory. So the number, roughly number of this source theory is 10,000 out of the total 600,000 theories. Also, in this Higgsing phase, there are maximal Higgs phase, which turned out to be the 8 number of them. And this matches with the F-theory results in this paper. So I don't show all the plot, but for instance, actually most theory goes to nothing, no gauge group, and some theory goes to the SO8 gauge group without any matter, and some goes to SU3 without matter, and some goes to the F4 gauge group without matter, and blah, blah, blah. So we are able to understand what is the possible dimension of the gauge group and rank of the gauge group for each cases. Okay, then let me go to the second part. So now we have understand the number of the supergravity landscape plus number of the super string landscape is this number. If we focus on the T=1 and without some problematic gauge group. The next question is that all of them can be coupled to the quantum gravity or not. So this is the second question. The answer is no. And the reason is that we have the bound from the supergravity string. The idea is as follows. So using the completeness hypothesis principle, and in the presence of the two-home gauge field, there must be the string which charges under it. And if there is this coupling, this B2 field itself is not gauge invariant. So this term gives rise to a gauge non-invariant term, which must be cancelled by the anomaly on this theories on the string, 1 plus 1 dimensional theories. The point is that from the anomaly inflow, we can compute what the central charge on a 1 plus 1 dimensional theories. while this 1+1 dimensional theory must contain the free contribution from the center of mass degrees freedom and current algebra contribution and so on. So that means that we have this type of inequality. So current algebra contribution it must be smaller than the inflow contributions. In any case, from this type of consideration, we can have this type of inequality. So left-hand side is this CG, current algebra part, and the right-hand side is that central charge computed from inflows. Also, there is yet another consistency condition proposed in this paper. So, okay, I don't talk about the detail, but there are two conditions. So there is a constraint on the conformal weight of the vertex operators, and for the existence of the affine Lie algebra with rep R, we have this type of condition. Okay, I don't talk about the detail, but the point is that if we specify what the matter field, we can compute everything, and we can impose a bound. And one thing I want to note is that theories with exotic representation is tended to be excluded because it tends to be give rise a large number of the second Cashmere's and a large number of the Minsky level. Okay, but let me show what's the result. So using this bound, we can exclude many theories. Like using this type of the bound, we can exclude theories with S-unit gauge algebra with fundamental plus symmetric representation. For instance, yeah, there are models which contain this representation whose number is 80,000. Okay, all of them are excluded. And also, this type of the bound excludes this gauge group and matter representation. So this is just a very specific one. But the point is that we can exclude many of the theory by imposing this type of bound. And there is yet another example. Okay, all of them are excluded by using the previous bound. So what's the result? The result is the following. So out of this number of the theory in a EFT landscape, more or less 20 or 30% of them are excluded by using a bound. This is a bound. And yes, this is our result. But we are not sure this is the end of the story, but still we are not sure if all of them can couple to the quantum gravity or not. For instance, there is one theory which I don't know how to realize in string theory. Now, this is a theory in this is a theory in this region. So that means that this is a theory which is still not yet to be excluded. So this is the theory is SO32 times SO8, and matter representation is as follows. So this is completely okay from the EFT perspective, but I don't know how to realize it string theory. So for instance, any geometric construction like F theory does not lead to this because any geometric construction gives rise to one neutral hypermatch plate corresponding to the volume of the internal manifold. But this theory does not have a neutral hypermatch plate, so I don't know how to realize it. So also, I'm not aware of the non-geometric construction like asymmetric orbifold realizing this. I don't know if this has a string construction or this will be excluded by the new consistency relation. So this is an open problem. So let me summarize my talk. So I have introduced my work about the classification of the 60 supergravities, and I talked about quantum gravity bounds. And the results are summarized in this plot. Okay, this is the end of my talk. Thank you very much.